Happy Hour. Today we're going to cover basic matrix operations and inverses. Okay, for basic matrix operations, we're going to do real life example, determine the dimension or size of a matrix, matrix addition, matrix subtraction, scalar multiplication, and applications problems. This is from section, I believe, 6.4. And then multiplying matrix and the identity matrix and inverse come from 6.5. Okay, so let's start with matrices. Matrices are important in the fields of management, natural science, engineering, and social science as a way to organize data. Example 1. Okay. The Easy Life Company manufactures sofas, armchairs, in 3 models A, B, and C. The company had regional warehouses in New York, Chicago, and San Francisco. In its August shipment, the company sends 10 Model A sofas, 12 Model B sofas, and 5 Model C sofas, and 15 Model A chairs, 20 Model B chairs, and 8 Model C chairs to each warehouse. So this data might be organized by listing them as followed. Okay, this is the sofas, right? We have 10 Model A's, 12 Model B's, and 5 Model C's. And the chairs are going to be 15 Model A's, 20 Model B's, and 8 Model C's. It can be done in this form or in a tabulated form, right? These are the models, A, B, and C, and here's the furniture, sofas and chairs. Also, it can be done in a matrix. Say, for example, right, matrix M, right? We can have 10, 12, 5, 15, 20, and 8, right? This is the same information that's here. But here, guys, the rows refer to the furniture and the columns refer to the models. Okay, it can be done in this form also. Okay, now matrices. So you have matrix A and matrix B. Matrices are denoted by capital letters, like for example, matrix A and matrix B, right? Capital letters. And the lowercase letters are called elements or entries. Okay, so for example, A11 means the 11 means the first row, first column. The 12 means first row, second column, and so forth. Same thing with the B matrix. Okay, this is my first row and the column, right? So this is called the position of an element. For example, A11 means, like I said earlier, means the first row, first column. A14 means the first row, fourth column. A23 means the second row, third column. Okay, now in this example here, what is the position of the following elements? A13, right? A13 means the first row and third column, so that means it's going to be 3. That's the entry. A24 means, right, the 24 stands for second row. Fourth column will be where the 8 is. That's the position. Now comes matrix dimensions, or the sizes of a matrix. The size of the matrix are the rows by columns. The number of rows, X, number of columns, right? So for example, determine the order of a matrix, right? This is 2 rows and 4 columns, so the size or the dimension is a 2 by 4 matrix. Example 2, determine the dimension of the matrix. Right, first of all, right, this is going to be 3 rows, 1, 2, 3, right, and 3 columns. So that's going to be a 3 by 3. The one in the middle is a 3 by 1, right, because we have 3 rows, 1, 2, 3 rows, and 1 column, so it's going to be a 3 by 1. And the one on the right, it only has 1 row, right, 1 row, but it has 3 columns, so it's going to be a 1 by 3. Okay, on this one, determine the order of the matrix. Okay, what is the order of the matrix, right? So how many rows? We have 1, 2, 3, 4 rows. How many columns? We have 2 columns, so 4 by 2. So this matrix is a 4 by 2 matrix. Okay, now comes, I believe up to this point, it has been straightforward, right? So now comes matrix operations. Right here, guys, means, right, if you have matrix A, right, you're going to go from row 1 all the way to the nth column. And in a similar fashion, right, you're going to go all the way from the first, all the rows, right, to the nth row, right, which means it can be like, whatever the size it is, it doesn't matter. But what matters here, guys, is in order to add or subtract matrices, they must be the same size. Okay? That's why I put it in red, must be the same size. For example, A plus B means you can add each same position from each matrix. For example, it was going to be A11 plus B11, A12 plus B12, and whatever's in B12. A13 plus B13, all the way until you get to the final column here. In a similar fashion, right? You can add the second row, first column, plus the one on B, the second row, first column, and so forth. You can repeat the process until you get to the nth row, right? And whatever row it is, and the nth column, all the way to the end. Okay, it's better if we do it by example. Okay, because at times the way they explain this on the book, or also from the author, it's a little bit at times as a student doesn't understand, it's a little bit challenging. But by doing an example, it's going to make much more sense. Okay, now this is the definition that's in the book. Matrix addition: the sum of two m by n matrices x and y is a m by n matrix on the x plus y, in which each element is the sum of the corresponding element of x and y. Same thing with the subtraction. Okay, all this means is what I'm going to show you on the next slide. Okay, example: matrix A is a 2 by 3, matrix B is a 2 by 3, and matrix C is a 2 by 2, and matrix D is a 2 by 2. Can we add A plus B? Yes, we can, because they have the same size. So the definition means that I'm going to add the first column and the first row first column on matrix A plus the first row first column on matrix B, and then first row second column on matrix A plus first row second column on matrix B, right? And you keep going until there's no more. For example, the last one on the first row is going to be the 2 and the 1, and then we repeat the process: 2 plus -1, 2 plus 3, and -1 plus 4. And the answer will be 7, -3, 3, 1, 5, and 3. This is the solution. You can go straight from here, guys, from the matrix A and B, right? You can go straight here to the answer. This step here, I just showed you what's taking place. Okay, but you can go like this. What's 1 plus 8 is 9. What's -3 plus 0 is going to be -3, right? And so forth. You can do it that way too. Now comes C plus D. Can we add matrix C and matrix D? Yes, we can, right? Because they're the same size, so we can add them. So it's going to be 5 plus 2, 1 plus -1, -4 plus 9, and 3 plus -7. Right, that's going to give us 7, 0, 5, and -4. That's your answer. How about, can we add A plus C? We have matrix A is a 2 by 3, and matrix C is a 2 by 2. So this cannot be done. Not possible. Why? Because they're not the same size. Again, in order to add and subtract matrices, they have to be the same size. Now to do the very same one, but instead of adding, we're going to subtract them. Right? So again, this is the size of each matrix. So A minus B is going to be the same thing as 1 minus 8. -3 minus 0. And 2 minus 1. And 2 minus -1. And then 2 minus 3. And -1 minus 4. And it's going to give us -7, -3, 1, 3, 1, -1, and -5. That's your solution. Now let's do C minus D. Right, it's going to be 5 minus 2, 1 minus -1, -4 minus 9, and 3 minus -7. The result will be 3, 2, -13, and +10. That's your solution. And can we do A minus C? Again, the answer is no, because matrix A is 2 by 3, and matrix C is a 2 by 2. They're not the same size. So it's not possible. Okay, not the same size. Now comes, it's called the scalar multiplication. Okay, so we have matrix X, 2, 0, 5, and 4, -2, -3. They want us to find 6x, 6 times matrix X. So it's going to be, the 6 is called a scalar. So we're going to multiply the 6 times every element in the matrix. So it'll be 6 times 2, 6 times 0, 6 times 5, 6 times 4, 6 times -2, 6 times -3. And here's the solution, right? It's going to give us 12, 0, 30, 24. What did I do here? -12 and -18. I don't know what I pressed here, guys, but let me see here. Oh, here we go. I'm sorry about that. So now it says find negative x. So negative, it means negative times matrix X, -1. The same thing as -1 times every element in matrix X. -1 times 2 is -2. -1 times 0 will give us 0. -1 times 5 will give us -5. -1 times 4 will give us -4. -1 times -2 will give us a +2. And -1 times -3 will give us a +3. Here's my solution. Okay, now comes, let's do this example here. Okay, it's called, example 6. Okay, they want us to do -4a for 1. For 2, it's going to be 5b, 5 times matrix B. And for 3, you're going to combine both answers, -4a plus 5b. Okay, so -4a means I'm going to multiply -4 times every element in matrix A. So it's going to give us, right, -4 times -2, -4 times 0, -4 times 5, and -4 times 3. It's going to give us 8, 0, -20, and -12. Now let's do number 2, 5b. It means 5 times every element in matrix B. 5 times 0, 5 times 2, 5 times 4, and 5 times -6. Here's the result will give us 0, 10, 20, and -30. Now for part 3, it's going to be what we got the answer from 1, right? Plus the answer in 2 and number 2. So -4a, it was 8, 0, -20, and 12. Plus 5b, it was 0, 10, 20, -30. Now we're going to add them, right? So now we're going to do what we did at the on the first example that we added matrices. So 8 plus 0, 0 plus 10, -20 plus 20, -12 plus -30. Going to give us 0. I'm going to give us 8, 10, 0, and -42. Here's my solution of -4a plus 5b. Okay, now remember the example that we did earlier, the first example for it was like a real life situation. Now it continues now, okay? So it says here, the Easy Life Company manufactures sofas, armchairs in three models, A, B, and C. The company has regional warehouses in New York, Chicago, and San Francisco. In its August shipment, the company sends 10 Model A sofas, 12 Model B sofas, and 5 Model C sofas, and 15 Model A chairs, 20 Model B chairs, and 8 Model C chairs to each warehouse, right, to the warehouse in Chicago, New York, and San Francisco. Now, it says here, right, for the second part, during August, the Chicago warehouse of the Easy Company shipped out the following numbers of each model, which the entries in the matrix have the same meaning as given earlier. So they want to use K for the models that were shipped out, right? So this is the C stands for Chicago, so it's going to be, right? So how are we going to know how many are left, right, after these were shipped out? So what was the Chicago's warehouse inventory at the end of September? Take into account that only the numbers of items received and sent out for the month what was given. So in this case, right, this is what the Chicago warehouse has. So it's going to be C minus K. So the C, right, which stands for Chicago, is what's in storage right now at the Chicago warehouse. And K stands for the furniture that the Chicago warehouse shipped out. So there's my the Chicago warehouse, right? It has all those models of furniture, and here's what they send out. So what will be left at the warehouse in Chicago, right, is going to be subtraction, right? So it's going to be 10 minus 5, which is 5, 12 minus 10, which will be 2, 5 minus 3, which will be 2, 15 minus 13, which will be 2, 20 minus 12, which is 8, and 8 minus 8, which would be 0. So this is what was left at the warehouse, okay? And if you go back, these are the sofas, right? So what was left was 5 Model A sofas, 2 Model B sofas, and 2 Model C sofas, and 2 Model A chairs, 8 Model B chairs, and there was no Model C chairs left. That's what it stands for. This is how you apply, like in a simple way, matrices to real life situations. Okay, now comes matrix product, which is the product of multiplying matrices. Okay, now it is very important. This is very important information that I'm going to share with you guys. So you have matrix A, right? Matrix A is an M by N matrix, and matrix B has to be an M by P. In order for you to actually multiply these two matrices, the two in the middle must match. They must be the same number. And the answer will be the outer, will be an M by P matrix. Okay, now, there's a question. If the size of matrix A is 2 by 3, then matrix B must be what? Has to be a 3 by something, right? Because the two in the middle numbers have to match. So it has to be a 3 by something matrix. And the answer will be a 2 by whatever the number is over here on the right. Again, the two in the middle must match for you to be able to do the operation on multiplication. And the answer will be the matrix, the size of the matrix will be the outer numbers. Okay? Now, this is number 7, example number 7. It just says, given the following matrices, state whether the matrices can be multiplied. We have matrix A is a 2 by 3 matrix, right? And matrix B is a 2 by 2, and matrix C is a 3 by 2. Can we multiply matrix A times matrix B? And number 2, can we multiply matrix B times matrix A? And for number 3, can we multiply A matrix times C matrix? So for number 1, it is not possible. Why? Because matrix A is a 2 by 3, and matrix B is a 2 by 2. Right? The two in the middle numbers do not match. So this cannot be done. Now let's try number 2. Matrix B is a 2 by 2, and matrix A is a 2 by 3. Can we multiply them? Yes, we can, because the two in the middle, they match. And the answer will be a 2 by 3 matrix. That'll be the solution, the size of the matrix. Next one, number 3. Number 3, we have matrix A is a 2 by 3, and matrix C is a 3 by 2. Right, the two in the middle match, so yes, this can be done. And the answer will be a 2 by 2 matrix. Let me just do an example here. Remember, this was matrix A and matrix B from the previous slide. Right, so matrix B is a 2 by, right, is a 2 by 2, and A is a 2 by 3, right? So yes, it can be done. And the solution for the matrix is going to be a 2 by 3 matrix. Okay, now this requires about 6 steps. The bigger the size of the matrix, the more steps it's required. Step 1, right? Here's what you got to do. You have to multiply every row times every column. That's why, guys, I put it here like color coded. I'm going to start with the first row. I need to multiply the first row times column 1, column 2, and column 3. Okay? So each one of these is a different step. So for the first step, we start multiplying row 1 times column 1. We multiply the first times the first and second times the second. So 1 times 2 plus 0 times 4, the answer will give us 2. So the 2 goes first here on the first row, first column. Then comes step 2. So step 2, I need to multiply the first row now times the second column. Again, I use color code, that way you guys see exactly what you're multiplying. So 1 times 0 will give us 0. 0 times -2 will give us 0. So 0 plus 0 will be 0. So the 0 goes here on the first row, second column. Now finally, step 3, we're going to multiply the first row times the last column. 1 times 5 plus 0 times -3. The answer will give us 5. So the 5 goes on the third column, first row, third column. Now we go to step 4. If we notice, we're done with the first row times every column on the second matrix. Now means that we're going to be using the second row and repeat the process by multiplying the second row times the first column, second column, and third column. Here's my first column. So 4 times 2 is going to be 8. -2 times 4 will give us -8. When we add them, it's going to give us a 0. So the 0 goes on the second row, first column. Then we do step 5. Okay, now it's going to be the second row times the second column. It's going to give us 0 plus 4, which will give us 4. So the 4 goes on the second row, second column. And finally, we come to the last step, which we multiply the second row times the last column, which is column 3. They're going to give us 4 times 5 is 20, and -2 times -3 is 6, so the answer will be 26. So that's my last entry, which will be on the second row, third column. So this is my solution. 205, 04, 26. Okay, now comes the identity matrix. Okay. I put here, recall from section 1.1 that a real number 1 is the identity of elements for multiplication of real numbers. Why? Because if you multiply A times 1 or 1 times A, it's going to give you the same number. In this section, an identity matrix is called the I matrix. It stands for identity. It's defined that has a property similar to those of the number 1. Okay, now the matrix A, right? We have matrix A times the identity will give you the identity. Will give you the matrix A. Again, matrix A times the identity will give you the same matrix. And right now, I'm going to prove it to you guys, what this means. Okay, example. If you have This means if you have a one by one matrix, the identity is 1. If you have a two by two matrix, this is your identity 1, 0, 0, 1. If you have a 3 by 3 matrix, this is your identity 1, 0, 0, 0, 1, 0, and 0, 0, 1. If you notice, all the ones are here, diagonally. And if it's a 4 by 4 matrix, it'll be the same thing, right? All the ones will be the diagonals, ones and the rest zeros. Okay, now, example number 9. See, we have matrix A, right? It's A, B, C, D. And the identity for the 2 by 2 matrix is 1, 0, 0, 1. So if according to the formula, right, or to the rule here, if I multiply matrix A times the identity, it's going to give you the same matrix. Okay, here we go. So step 1, right? I'm going to multiply the first row times every column. So A times 1 plus B times 0. The answer will be A plus 0. The answer will be A. So the A goes here on the first row, first column. Now comes step 2. I'm going to multiply the first row times the second column. Right, times the second column is going to give us A times 0 will give us 0. B times 1 will give us B. So 0 plus B will give us B. So the B goes on the first row, second column. Now comes step 3. But if you notice, we're done with multiplying the first row, right, times every column. So now we're going to switch to the second row. That's why it's in blue. Times the first column, so it'll be C times 1 plus D times 0. Which will give us C plus 0. The answer is C. So C goes on the second row, first column. And finally, step 4, we do the second row times the second column. It's going to give us 0 plus D. The answer will be D. Because if you notice, guys, we got the same matrix. So the identity, which is for a 2 by 2 matrix, is 1, 0, 0, 1. If you multiply the matrix times this identity, the answer will be the same matrix. That's what this definition is trying to explain here. Okay, now let's do the inverse. Getting the inverse of a matrix, there's like 2 ways to do a 2 by 2 matrix. Okay, which I'm going to show you both ways. But first, here, guys, it says here, recall that for every non-zero real number A, the equation AX equals 1 has a solution, namely, which is 1 over A is called the inverse. Similarly, for the square matrix A, we consider the matrix equation AX equals to the identity. The equation does not always have a solution, but when it does, we have a special terminology. If there is a matrix, right, this means if there is an inverse matrix, A to a negative 1 means that this is the inverse of matrix A. So if you multiply the original matrix times the inverse, will give you the identity. The inverse is called the inverse matrix. Okay, example. Given matrix A and B, determine whether B is the inverse of A. Okay, here's my solution, right? The solution is B is the inverse of A if A times B gives you the identity. So we can find the product, right? So if we multiply these two, matrix A and B has to give me the identity to be 1, 0, 0, 1 for it to be the inverse. And if it doesn't give you the identity, B is not the inverse of A. Okay, so let's find out. Right? So this is my identity. You have to get this right here. Right? That's the identity. So if we get that right, B is the inverse of A, right? But anyway, guys, you can try this with a multiplication, guys, by multiplying them out. This is what you get, 1, 0, 0, 1. So we know that A and B have is an inverse, that B is an inverse of A. And why? Because when you multiply them, we got the identity. Okay, now let's find the inverse of a 2 by 2 matrix. Okay, So for a 2 by 2 matrix, we have matrix A is 1, 4, 2, 6. That's matrix A. So we have to find the inverse. Okay, if you notice, for the inverse, 1, 0, 0, 1 is the identity. So we're going to use the Gauss-Jordan method. Right? This was explained in section 6.2. Right? So eventually, you have to go from 1, 4, 2, 6, right? And 1, 0, 0, 1. What's here on the right side, the 1, 0, 0, 1 has to come to my left side. And then whatever I have in the right side, this will be my inverse. But you'll be thinking, how? Right? How are we going to do it? So this is my inverse. Here's how you do it, okay? Let me show you the steps. Okay, now you guys remember, guys, that by using the Gauss-Jordan method, that the first step is that this one here has to be a 0. The 2 must be a 0. So we're going to use row 1 to make the 2 a 0. So I'm going to multiply -2 row 1 and add it to row 2. Right? So we're going to keep row 1, and here's my work for -2 row 1 plus row 2. So -2 row 1 means -2 times every element in row 1, which is 1, 4, 1, 0. Here's going to give us -2, -8, -2 and 0, because -2 times 1 will give us -2. -2 times 4 will give us -8. And -2 times 1 gives us -2. And finally, -2 times 0 will give us 0. Then I'm going to add it to row 2. So row 2, all we do is bring it over. So we get 0, -2, -2, and 1. So this is my new row 2. Okay, now comes the second step. Now with this -2, I gotta make that the 4 a 0. That means that the 0 must be the 4 must be a 0. So I'm going to multiply 2 row 2 and add it to row 1. So we're going to keep row 2, and now we're going to do 2 row 2 plus row 1. And again, why did we use 2 for? Because 2 times -2 will give us -4. And then when added to 4, they'll cancel. They'll be eliminated. So 2 row 2 gives us 0, -4, -4, and +2. And then row 1, all we do is bring it over. Then we add them. So we get 1, 0, -3, 2. So this is my new row 1. If you notice, we're almost done, right? But the -2 cannot be -2. It has to be a 1. That means I'm going to multiply the row 2 by the reciprocal, which would be -1/2. So -1/2 row 2 means we're going to be multiplying -1/2 times 0 will give us 0. -1/2 times -2 will give us a 1. -1/2 times -2 will give us a +1. And -1/2 times 1 will give us a -1/2. If you notice, this is my inverse. Okay. Okay, now, here's another way to get the inverse. I think this is easier than the method I just showed you guys. For this method, we have to use a specific formula. Say this is matrix A. Matrix A is A, B, C, and D, right? These are my entries or my elements. To get the inverse, you're going to do 1 over the determinant. The determinant is A times D minus B times C. And then here, guys, the A and the D, you switch places. D goes to the place where A is, and A goes to the place that D was. And for the B and the C, all we do is change signs. Okay, so this is my formula. So let's do, I think, the very same one as before. I think it was the same one, yeah. So here, guys, right? Here's my, right? So the inverse is going to be 1 over 1 times 6 minus 4 times 2. And here, guys, the 1 and the 6 switch places, right? Which is the A and the D location. We switch places. And the B and the C become opposite signs. They will become negative. Now, if you notice, This is the same thing as 1, right? It'll be 6 minus 8, which will give us negative 1/2. So you multiply that negative 1/2 times the 6, negative 4, negative 2, and 1. If we do that, it's going to give us what? Negative 3, positive 2, positive 1, and negative 1/2. Here's my solution. Here's my inverse. Okay, now it gets a little bit more challenging when the size goes over a 2x2 matrix. Like, for example, a 3x3 matrix is a little bit more challenging. And I believe last week during our Friday happy hour is where I explained the Gauss-Jordan method. So we're going to do it again. Okay, but this time it's going to be a little bit more with more elements. So it's going to be right, the matrix A and its identity. So now the objective is for what's in the right, the 1 0 1 0 0 0 1 0 and the 0 0 1 to come to my left side, and whatever's left on the right side after I do all the operations will be my inverse. Okay. Again, recall from 6.2 the Gauss-Jordan method. So here, guys, right? So this is my inverse, but how do we get this? Right, that's your inverse. Okay, again, we have to use the Gauss-Jordan method, and here it is, similar to what I did last week. So here, guys, right? It's gonna be like 3 steps. Step 1, I'm gonna keep row 1, and where the 2 is, the second row, first column, and the third row, first column, these 2 must be zeros, right? So I have to use row 1 to change row 2 and to change row 3. So for example, if I multiply negative 2 times row 1, we'll guarantee that it will cancel the 2 there, because negative 2 times 1 will give us negative 2, and then when added to row 2, this place will be a 0. So we're going to be negative 2 row 1 plus row 2. And to eliminate the x, the 5, right? Where the 5 is, the row first column, you're going to multiply for the first row by negative 5. So it'll be negative 5 row 1 plus row 3. And here's my work. Right? Negative 2 row 1 will give us negative 2, 0, negative 2, negative 2, 0, and 0. Plus row 2, all we do is bring it over. It's going to be what? 2, negative 1, 0, 1, and 0. After we add them, we get 0, negative 2, negative 3, negative 2, and 1. So this is my new row 2. Now negative 5 row 1, right? We're going to multiply negative 1 times every entry in row 1, right? It's going to give us negative 5, 0, negative 5, negative 5, 0, and 0. Plus row 3, all we do is bring row 3 over, and then we add them, right? So this is what we get: 0, 0, negative 5, 0, and 1. So that's my new row 3. Now, if you notice, for step 2, right, these 2 are already zeros. So we can bypass step 2 because it's already completed, and we can go to step 3. See, it's already done, because step 2 of these must be zeros. So we go to step 3, right? For step 3, the 1 has to be a 0, and also the negative 3 has to be a 0. So we're gonna keep row 3, right? And that's a row that we're gonna use. So here, right, we got a negative 5 here on row 3. We got a 1 there. That means that I'm gonna add row 3 plus 5 row 1. And then since these are both negative, I need to multiply one by a positive. So I'm going to multiply negative 3 times row 3 and add it to 5 row 2. And here's my work. Row 3 equals to 0, 0, negative 5, 0, 1, plus 5 row 1, right? I multiply 5 times 1 will give us 5. 5 times 0 will give us 0. 5 times 1 will give us 5. 5 times 1 will give us 5. and 5 times 0 and 0 will give us 0, 0. After we add them, we get 5, 0, 0, 0, 0, 1. That's my new row 1. Then finally, right, we're going to multiply negative 3 row 3, which gives us negative 3 times 0, 0, negative 5, 0, and 1 gives us 0, 0, 15, 15, 0, and negative 3. Then we're going to add it to 5 row 2. So we're going to multiply 5 times every element in row 2, which is 0, negative 2, negative 3, negative 2, and 1 and 0. So after we multiply 5 times every element, it gives us 0, negative 10, negative 50, negative 10, 5, and negative 3. After we add them, it's going to give us 0, negative 10, 0, 5, 5, and 3. So that's my new row 2. But if you notice, all these are complete, right? All these are zeros and these are zeros, but these are not ones. They have to be positive ones. So that means I'm going to multiply row 1, 1/5 times row 1. And negative 1/10 times row 2. When you do that, that's what it gives us. And I'm going to multiply negative 1/5 times row 3. And here's my solution. By multiplying negative 1/5 times every element in row 3, that's what we get. So guess what, guys? This on the right side is my inverse. Let me go back. Yeah, guys, this is my inverse. The inverse will be, the inverse will be 0, 0, 1/5, negative 1/2, negative 1/2, 3/10, 1, 0, and negative 1/5. This will be your inverse. And I believe that's it for this presentation. Hopefully, this will help you with the section for this week, with the sections. And I believe next week, I'll be going over the exam review for chapter 6.
Thank you, Mr. Isasi, for the wonderful presentation. We want to remind you all about our previously recorded sessions, which are available on YouTube on the Tejano Virtual Events playlist. This session will always be available on the playlist later on today. Also, linked is a short survey to help us improve our Tejano Virtual Events sessions. Please take a moment to fill out that survey. Before you leave, I want to share the Tejano Virtual Events flyer with the sessions that we will have next week. At 1 p.m. today, we're going to be having the dog fostering with Liz Olivas. We will be back with Happy Math Hour next week at 11, where in Math 1314, we will be covering linear and nonlinear systems. And in Math 1324, we're going to be covering the Exam 3 review. Our 1 p.m. session next week will be on EPCC student clubs. Thank you all for coming in today. We hope that you have a lovely weekend. If you have any questions, please feel free to use the chat box or your mic. We hope to see everybody again for the Happy Math Hour next week. Have a great day.
Thank you, guys.